All right, we're going to do our second lesson in our basic probability. We're going to learn about this thing called the law of large numbers. And what does that mean? And what does that mean in terms of all probability? Well, let's take a look. So first, we're going to do a little activity. And I think even if you are not doing this in class with us, I think it'd probably be pretty fun for you to do this. What you're going to do is you're going to flip your coin, and you're going to keep track of how many times your coin lands on heads. Okay? Then we will keep track of that cumulative probability. So here is, and then we will plot that relative frequency. So here's what that will look like. So here's what you got here. And we're going to be doing that cumulative number of heads. So here is the first trial. So you're going to flip your coin, okay? And then you are going to either get a heads or a tails. I got tails. So since that means I got tails, then I start here at 0, because 0 out of 1 heads. Now, if you got heads on the first coin toss, then you'd be starting up here at 100%, because 1 out of 1 times you got heads. All right. Then you flip it again. Okay? And so I got heads. And so that means that now I have gotten one of the heads out of the 2 trials. So there I am at 50%. Let me do one more. Actually, I'll do 2 more. So look, I got heads again. So now I have gotten heads twice out of 3 trials. So there I go to that. Okay, so watch this. Here's how this next part works. Here I go. Oh, I just got the next one. I got tails. Okay, so I got tails. So that means I had no increase in my number of heads. I'm still at 2 heads out of the 4 trials. So I'm back down to 50%. And lo and behold, here's tails again. So I'm now staying at 2 heads out of the 5 trials. So I'm down to 40%, and so on. So I want you to plot to do your amount and see what you end up with by the time you flip your coin 20 times. Okay, so pause and try that and see what comes out. All right, so after you have done that, then let's take a look at what does this really mean? What does this show us? Well, let's talk about it. You, of course, were doing an experimental probability. You were performing an actual experiment, okay? So let's talk about, what do you expect to end up in the long run as we do many coin tosses about what percent of the time we're going to get heads? Well, of course, that's 50%, okay? So that is theoretically what we expect to happen. That's the predicted, okay? So what's expected is what's predicted, and that's theoretically what happens. All those things are the same thing, okay? Now, then we do our experiment and we see where we end up. Well, where we end up is our experimental probability, and that's what actually happened when we performed the experiment. Okay, so think residuals that we are just coming from our past unit, that where we were comparing actual from the predicted to see how far off we were. So that's something that's really important that we're going to approach, and why we want to go through this probability. We want to see how far off is what actually happened from what was predicted to happen. So then we can next semester gauge in, okay, well, what's happening that's making it, whoa, that should not have happened. That was unusual. That was not expected. All right, so I ended up with 45 out of 20. Now, so I'm going to keep track of some information tomorrow. What's going to be interesting is I'm going to keep track of, or when I do my notes there, I'm going to keep track of how many of my students end up in each one of these sections. So I'm going to see, how many of them ended up at 45, how many ended up at 50%. So we're going to see at the end of the day, and maybe I'll reveal that to you in tomorrow's video, what percent of people ended up at each one of these, and look how many people ended up with 100%. How many would it end up with 100% heads? How many? Probably nobody, And what's interesting is we're going to see that most people had cumulative proper probabilities. It was more common to end up here in this central location than it was to end up out here on the outside edges. So look forward to seeing those results. All right, here we go. Next, what's happening? So what did you notice? What happened to your cumulative probability of getting heads, and what happened? So I said as there became more and more trials, as I was going more and more, then that experimental probability kind of settled down and it got closer to that true theoretical probability that we expected. Now, this is kind of the new thing that you are learning, that this has got a name. Not, let's see, I think this may be the only theorem that we have to know by name. And so this one is law of large numbers. Actually, I think there's one more. I can't recall it. But by name, we have to know what the law of large numbers tells us. Oh, central limit theorem. That's the other one. Law of large numbers, though. This one tells us, law of large numbers says that as you do many, many trials, I mean, we're talking many. We're talking like hundreds and hundreds of coin tosses. As you do many, many trials, then that cumulative probability is going to get closer and closer and closer to the theoretical that we expect it to be. And so we're going to settle down to that 50%. All right, I have a song for that, of course. If you do many trials, many, many trials, the cumulative probability, it will settle down to the true probability. The law of large numbers, you see. Casinos bet on the law of large numbers. I'm telling you, if they know that the probability of this, and they can set slot machines to have a certain probability of frequency of payouts. So they will set those slot machines to pay out so much percent of the time. And as people play over and over and over and over and over again, it will happen that frequently in the long run. And in doing so, then the casino knows that they will win more frequently than they lose. And so, therefore, the casino knows that over time, they ultimately win. Okay, a single person might come out ahead, but in the long run, the casino knows that it will win. All right, let's take a look at this example and kind of talk about some things, other components in real life that kind of bank on the probabilities. Insurance companies. So insurance companies collect annual payments for fire insurance and lots of kinds of insurance from homeowners in exchange for paying to rebuild a house if it burns down. Well, why should you as an individual be reluctant to accept a $300 payment from your neighbor to replace his house should it burn down during the upcoming year? Well, I think that is a bit obvious. You, in taking in money from only one neighbor, $300. Okay. And, you cannot replace an entire house if it happens to burn down. I mean, and it's not very likely, but it could happen. Okay. But insurance companies, of course, they can take in they have many, many, many clients. They have many, many, many clients. And so they know that they're going to be taking in much, much, much more money than they will be paying out. Because one of the main jobs that statisticians do is called an actuary. Actuarial tables are created from data, and statisticians create these actuarial tables that then companies will set their fees on. So they know the probability of homes in this area or in this area or in this area, the likelihood of them having tornado damage or having fires or whatever it is. So they know the probability of hail damage to roofs, all those kinds of things. And so then they will base the premiums that you have to pay to insurance on how frequently they expect in the long run over the course of many, 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 many clients, how many of those payouts they expect to happen. All right, that's how insurance companies make their money. So now, if you're flipping a coin and your first 5 coin flips are heads, what's the probability that that next one's going to be heads? Should you say, woo, I'm on a winning streak? I think I should bet on it being heads because it's more likely to be heads because I've been doing so many of those coin flips being heads. No. Next flip is independent of the previous ones, regardless of what has happened. The probability is still at 50%. So it's not meaning anything. You know, you're going to be a hot streak. Are you on a hot streak? Or let's see, what does it say? Should you bet if you're on a hot streak, or should you bet the next coin that you are owed a tail because that average has to, that probability, that theoretical has to average out? Well, again, neither. The probability of this next coin flip being heads is 50%, regardless of what has just happened 800 times ago, or these last 800 coin flips. Okay? Independent. The fact that I got whatever I got before does not change the probability of me getting a heads on the next coin flip. Okay? So, sure, you get a whole bunch of heads in a row. Well, the law of large numbers says many, 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 many trials. So that's going to be a long time. Okay? We're talking many of those. All right. Last topic. We want to discuss this connection between disjoint and independent, okay? Because it is a big misnomer and a big misunderstanding that those two things are related or have to do with each other. Or a lot of times people think that if you have disjoint events, then they are independent of each other. Okay. So in order to know what the relationship is between disjoint and independent, we have to break it down into its fundamental definition. And by breaking down into its fundamental definition, then you will see the results that we're about to discuss, and in summary, what the relationship is between disjoint and independent events. So here we go. Actually, I think I have a deck of cards right here. I do. I'm pull out my deck of cards because we're going to use an example with decks of cards. So here we go. Okay, well, first of all, we know our definitions. Disjoint events have no outcomes in common. And we know that independent, when the fact that you are one thing does not change the rate. Okay, so here I go. Got all my deck of cards. All right, let's do this. So we have scenario number 1. Scenario number 1 is going to demonstrate. So I'm going to say, okay, pick a card, any card, okay? And you are going to place a bet on whether or not you choose a red. The card you choose is red. So you pick a card. I'm not going to look at it. Okay. Actually, I did that wrong. I forgot. Okay, hold on a second. I got to rig this so it'll work out with my game. So what am I looking for? Oh, got it. Okay. All right. So here we go. Pick a card. Any card? Here's your card. I'm not going to look. Oh, I get to look. You don't get to look. I forgot. Okay, sorry. Pick a card, and I get to look at it. Okay, you ready? I look at it. Place a bet as to whether or not you think the card that you chose, and I'll look at it, is red. Okay? All right. So what do you think? What's your chances? Okay. Well, hopefully you know decks of cards. 50% are red. So 50-50 chance it's red. Okay. So are you going to bet? Who knows? Okay, but wait. I'm going to give you a hint. And maybe this will make you change your mind and decide to bet better or more or less maybe. Here we go. I'm going to give you a hint. Your card is an ace. So, what's the probability that it is red? Okay, so I'm telling you it's an ace. So, given that, and we're going to learn this later, so we'll learn this from this symbol. So, this line here, given that you have an ace, given that I'm telling you it's an ace, so what's the probability it's red? Well, how many aces are there? There are 4 aces. So I've now narrowed it down to these 4 aces here. But what do you know about these 4 aces? 2 are black, 2 are red. So what's the probability of this card being red? If I told you it's an ace, still 1/2. So what just happened? The fact that I told you it was an ace did not change the probability as to whether or not it's a red card or not. It's still 50-50. So look here. Therefore, let's discuss the concept of independence. Are these 2 events of picking a red and picking an ace independent events? Well, yes. Picking a red and picking an ace are independent because the fact that you picked an ace has no impact, does not change the probability that the card is red. Done. There we go. Now, let's look at the next one. Okay, so now we're going to discuss this. So the next question is, are the events picking a red and picking an ace disjoint? Okay, so definition, disjoint. No outcomes in common. No outcomes in common would mean you can't have a red and an ace at the same time. Okay, so can I have a red ace? Heck yes, you can have a red ace. So that means they have outcomes in common. No, not disjoint, because there are outcomes in common. You can have a red ace. So those events are independent and they are not disjoint. Independent, not disjoint, independent, and not disjoint. Just showed you that. Let's do another scenario. Here's our next one. All right. Ready? Here we go. Here's our cards. Okay? Pick a card, any card. You're going to pick a card. Oh, here it is. And you place a bet as to whether or not it's red. Okay? How much you want to bet? How much you want to wager? Okay? Well, probability of it being red is 50%. So you're not much better off or much worse off. Okay, but guess what? I'm going to give you a hint. Another hint. So this time, I'm going to look at your card. This time, here's your hint. It is a spade. What has just happened? What do you now know about this card and it being red? Well, if you know decks of cards, you now know that the probability of having a red is now 0. So your hint's going to make you say, whoa, I want to bet against it being red. So look at right there. Red is a half. But then if I told you it was a spade, there are 0 red spades. Oh, I said space. I meant spade. If I tell you it's a spade, so there's now a 0% chance of having a red and a spade, or a spade that is red. So therefore, now, are having a red card and having a spade independent? Is the fact that you are one thing going to change the rate or not change the rate? If it's independent, it does not change the rate. Well, what just happened? From here to here, probability went from a half to 0. The fact that you are one thing just changed the probability to 0. Therefore, they are not independent, because the fact that the card is a spade changes the probability of the card being red to 0. Okay, not independent, not independent. Okay, but let's talk that other definition, disjoint. Are picking a spade and picking a red disjoint events or joint? Is there something that could happen? Can they have happen in common? Are there red spades? Okay, guess what? They are disjoint because picking a red, there are no outcomes in common. Did I say that right on the previous page? For some reason, I think I said that wrong. Hold on. I'm now just second guessing myself. Look real quick. Let me just double check myself. Oh, I guess it was at the top of the next page. Oh, okay, okay. The red and the ace, there are outcomes in common. Okay, phew. Thought I had that wrong. Well, here, picking a spade and a red, there are no outcomes in common because you cannot have a red spade. So, it is not independent, but it is disjoint. The other one, we said, it's not independent, it's independent and it's not disjoint. So look here. Here's this summary. I've got it right here written because I confused myself and I can't say it right. So disjoint events, if they are disjoint, just like the one we just had, the red and the spades, they are not independent. Because the fact that you are one thing changes the probability of the other, changes the probability, so it's not independent. Disjoint events are not independent because the fact that you are one thing, they're disjoint, would change now the probability to 0. Okay? Now, if they are independent, then the fact that you are one thing does not change the rate. Well, then that means those two things can happen at the same time, and the fact that you are one thing does not change the rate. So they are not disjoint. So what you need to know is those two things are different. They are not the same. If you are one, you are not the other when it comes down to looking at those definitions. I know it can be confusing because you want to think that they're the same thing, but it's not. This was just a thinking map to kind of guide you through the ors and the and problems and thinking if you are disjoint or not. Because when we get to the section after Thanksgiving, then we're going to get into a little bit more complicated formulas and stuff. And so then we'll want to reference this back. But I guess for some reason, this shows you that understanding this idea of disjoint and independence is going to affect later on um, how we do the math and how we decide to proceed with finding our probabilities. All right, law of large numbers and disjoint versus independent. That's the deal. Now you get to practice more probability problems today because you have a quiz over your basic probability tomorrow. Good luck to you.